apart from the problems which I mentioned already, there will be a very short exposition on what is called the discontinuity of the specific heat in the Midfield approach. So if you have a theory of a phase transition with the symmetry Z2, like an Ising mode, and you lower the temperature and you want to calculate the singular part of the specific heat. The specific heat, being one of the thermodynamic measurable quantities, has to expose some kind of singularity. And this singularity is basically defined like this, when alpha is the coefficient, the critical exponent, which has to be found. Can be measured experimentally, but most importantly, must be calculable theoretically. So the Midfield theory gives you such an opportunity, but instead of some kind of smooth behavior, you will find something like this. So this is the specific heat. Let's say this is Tc, this is T, so it's low, it's decreases and then undergoes a jump upwards at Tc. So the limit from the left and the limit from the right don't coincide. There is a finite discontinuity. You can estimate it using the standard Landau expansion or simply Midfield approach, doesn't matter. So it is done, but be careful. In those nodes, you will find some typos or maybe even errors. The coefficients may not be correct. So please don't trust the numerical coefficients. These may be, I apologize. All right. So this remains for you. What we will do today is we'll talk a little bit in more detail about the Goldstone theorem and the Goldstone modes, which are associated with the lowest energy elementary excitations in systems undergoing phase transitions and possessing a discrete symmetry. Excuse me, a continuous symmetry, I mean, so. Goldstone theorem. So the first most important requirement is continuous symmetry. So the Ising model is not the model of this type because the symmetry is discrete. In the Ising model, the order parameter m is the average value of sigma. Sigma takes only two values, up and down, plus 1 or minus 1. And this is the global zeta symmetry which the Hamiltonian suppose like this exhibits in the absence of the external magnetic field, so you can invert the signs of all the spins and the energy remains invariant, doesn't change. This is the global discrete symmetry. I emphasize discrete because sigma cannot change continuously. It only has two allowed values to take, plus 1 and minus 1. So how can you pass to a continuous symmetry? You still think in terms of some order parameter, but this time you say that your order parameter is not a scalar quantity, but instead it's a vector with many components, right? So suppose you build up such a vector with n components. Right? It's an n component vector. So what do you want? You want to build up a theory or a phase transition, a Midfield-like theory of phase transition, where the order parameter takes a non-zero expectation value below some critical temperature. Whereas above this critical temperature, this order parameter is 0. This is a standard requirement because this is what the phase transition is about. The order parameter is a quantitative measure of order. Once it is non-zero, it's a function of temperature, of course. You are in the ordered phase. Otherwise, you are in the solid phase, high temperature phase. But how to incorporate the symmetry? This is the vector with n components. What you can do, you can rotate such vectors, right? As opposed to the discrete vectors, which can only be reflected from plus to -1, these can be continuously rotated. And the transformation which describes such rotation looks like this. Every time I write a pair of the same indices, it means that I'm summing over. When Rik, when R is a n by n matrix, satisfying this condition. In other words, it's a n-dimensional orthogonal matrix. That's exactly how it is. Well, if I choose the determinant of this matrix to be +1, this condition allows the determinant to take two values, +1 and -1. If I specify our discussion to the case when the determinant is +1, these will be proper rotations, just rotation, but not reflections, only rotations. And that's exactly what we are after. So under such rotation, the momentum, the components transform like this. And there is an invariant, m squared, defined as sum of the squares of all the components, which doesn't change. The length of the vector m is the same. It may change its own orientation, the length doesn't change. Therefore, if we want to build a free energy which depends on the order parameter n, and which possesses this continuous, this symmetry is called, by the way, SON. Generally, I can remove this. S means special. Special means determinant is equal to 1. If I remove this S, that means the determinant, the modulus of the determinant is 1. I will allow both sides, and this is included. The reflections must be there as well. But basically, and most importantly, we'll be talking about rotations. Right, so I have to build up an ON invariant for energy. We know that there is an invariant, which is just the square of the modularization. Therefore, the free energy density is a function of m should start, again, A is some alpha times tau. This is the general property of the Landau expansion, you remember that? Times, not that m scalar square, but m vector square. This is the first term of the Landau expansion. Now we would like to write down the fourth orbital. What you do precisely the same as you did before. It is 1/4 b, when b is a positive quantity. This is important. Here alpha is also positive. And here we take m squared and then square this square. Right, so you take the square of the length, square. In this way you get this fourth orbital, right? And then in principle you can continue, but to us, if b is positive, it's enough. Everything is stable. Right? And then you then assume that below to C, there exists this, the minimization of the corresponding free energy yields a non-zero value of the order parameter. Now, if you look at the equations of motion, minimizing this free energy, which means that I write down this set of equations for all components I, 1, 2, and so forth, n. What I will obtain, it will be mi, it will be a plus b sum over j from 1 to n, mj squared equals to 0. This is how the self-consistency equation that we already know very well transforms when you pass from the discrete symmetry to a continuous one. And again, above TC you have only one solution, all in E are equal to 0, this is this solution. And below TC you have the solution which tells you that this is actually the square, m naught squared, is minus a URE by b, it's alpha URE by b, tau modulus. Tau in this case negative, therefore it's minus tau modulus. So everything is very simple, not a big deal. It's a straightforward generalization of what we have learned for Z2 symmetry for the Ising model. So the case of the Heisenberg model, for instance, if I take n equal to 3, that means that I have a 3-component vector. It's a standard ferromagnet described classically. I'm not trying to invoke any quantum mechanical arguments. It's a pure classical description of a 3-dimensional classical vector. So if n is equal to 2, then I will have a planar vector, which only changes in some plane. There are some easy plane magnets in nature, as well as easy axes, and there also are fully isotropic ferromagnets with full SO3 group and with 3-component order parameter. So it is clear that the self-consistency equation fixes the length of this vector. I emphasize the length of this vector, but not its orientation. Right? Exactly as we had in the Ising model, we would say that the order parameter, the modulus order of the order parameter, is fixed the self-consistency equation, but not the sign. Whether all the speeds will be looking upwards or downwards, this is up to the type of spontaneous breakdown of the symmetry, and that is determined by an infinitesimally small magnetic field which needs to be applied to enforce the order parameter to choose one of the two allowed in degenerate pairs. But it's done, it remains in this position. Right? But now the situation is slightly more tricky, because, for instance, if my order parameter is a 2-dimensional vector, in other words, if n, small n, is 2, then I can write down my order parameter m with components m1 and m2 as modulus of m. And here I will write down cosine of some angle phi and the sine of angle phi. The standard angular coordinates. You are familiar with the planar geometry, right? And as follows from this exposition, everything depends on the modulus, and nothing depends on the angle. So there is a full degeneracy of the free energy with respect to rotations. So in other words, if I fix the length by this condition, I'm left with one more degree of freedom with the orientation. So if I say that I know the length of this vector, it doesn't mean that I know everything. I know something, very important part of everything, but not everything. To get information about everything, I have to build up the so-called the space of degeneracy of the other parameter. And then it's a circle, S1, where this angle phi varies from 0 to 2 pi. This is the space of degeneracy. I say degeneracy because for any direction of your magnetization, this or that, any, your state is now fixed by location of your vector on the circle. For any such value, the Frey energy remains the same. This is what is meant by degeneracy. In other words, your minimum energy state is degenerate, continuously degenerate in the sense I can vary the angle, I can very continuously change the total magnetization. It's a global rotation, global SO2 rotation of all the speeds, and nothing is going to change. Now, if I go to the case n equal to, okay, before I go to the higher n case, let me try to build up a profile of the free energy. So let me measure here F, which will depend on the length of this vector and on the angle phi, right? So what do? I do the following. Let me do it in the following way. This is the famous Mexican head potential. What it tells you? It tells you that the free energy has a minimum. So here I measure M1, right, or Mx, and here I measure M2 or My. This is the. This is how I. Measure the angle. I fix the location on this curve. This curve is just the bottom, but the bottom. So the local bottom of this profile is this point, but because of the extra O2 symmetry, I can make a rotation. I will find the narrow channel along which the representative point will move in such a way that the potential phi will not change. It's the same. So this is the space of degeneracy. This is that very circle S1 but shown here on this picture. So the energy does depend on the location on this curve. In other words, it's like a harmonic potential in the close to the minimum. You have some kind of phi m squared term, and then the system wants to order in such a way that the absolute value of m0 corresponds to the minimum. That's not all. It can also go run along this circle without changing any energy. This is precisely what Goldstone modes are about. These degrees of freedom are taken by the Goldstone modes. The thing which is absent in the Ising model, because the Ising model is a discrete model, and this is a continuous model. Now in a three-dimensional case, instead of this, you will say, okay, this is the manifold which is determined by this condition, and this is nothing but the equation of a sphere, two-dimensional sphere, whose radius is m0, right? So I can choose any direction of the vector of the fixed length m naught on the surface of the sphere, and all these points are equivalent from the point of view of energy. They correspond to the same energy, but they describe different states. So therefore, when moving from one direction to the other, you have to switch on all this mechanism of orthogonal rotations, but this time three-dimensional rotations. So it's clear then, just looking at this picture, that apart from something which has supposed to be kept because the motion of a particle within a potential well will always give rise to some oscillations with a finite frequency or finite energy. So therefore, with the formation of the length of this vector m naught, some finite energy should be associated. It's clear. Associated with the energy will be a corresponding length, because the length and the energy are related by the following formula. So delta is the characteristic energy, v is the characteristic velocity, then the length is given by this formula. It's easy to check. But on top of that, there should be another degree of freedom, another branch of excitations, which for a uniform rotation, the uniform rotation means that if I'm think in terms of the dispersion omega of k, that we put this g as a gold star, in the limit when k goes to 0, which means that the wavelength goes to infinity, that means that I'm talking about simultaneous rotation of all the speeds, the global simultaneous, as a whole, rotations of all the speeds of the system, then the system will run along this line. Only in that case. And the corresponding energy should be 0. Because I'm exploring all the degenerate states, it should not be any obstacle on the way from the shape of this potential. We see that every time you go along the radial direction, you do have an increase of energy if you deviate from the equilibrium. But if you go along this azimuthal direction, you are free. So therefore, it is clear that such branch of excitation should be associated with extra angular degree of freedom. And every time I have this kind of motion, in this case, I cannot draw anything like this because I don't know how to do a four-dimensional picture. I can't. Maybe you can, but I can't. Yeah. But qualitatively, it already tells me everything, what's going on, right? Now let us do some very simple calculations. You can find them in Cardy's book. This book is just excellent because it gives you an example of the way how smart people think. You don't expect from Cardy. Cardy is a heavy thinker, I would say, using heavy mathematics. Very strongly mathematically oriented, and all of a sudden he gives you a kind of hand-waving simple argument, and you admire the way he thinks. This is one of the straightforward ways to show the existence of these gold-star modes. So what you do is the following. So you assume that you are in the ordered phase. It's very important. The Goldstone modes exist only in the ordered phase with the spontaneously broken symmetry, not in the paramagnetic phase, no. So you assume that your M naught is the equilibrium value, and you know how to calculate this M naught. It's already been calculated. Now you want to consider excited states. Therefore, and then let M naught look as follows. Without loss of generality, I will choose the spontaneous magnetization to look along the first axis. So in case of two-dimensional vector, it will be the x direction, right? And now I will consider fluctuations that I will add here m. When m is a small vector whose length is much less than m. Why I'm doing that? I'm doing that because I want to understand what kind of excitations exist. From the picture that I had already with the Mexican head, I know that this direction, when I change the radius, this direction must be a heavy direction. Heavy in the sense that it will be costly to change the equilibrium value of the other parameter if I change the radius. But if I don't change the radius, I can go along this circle, and that should not be costly at all. And I would like to see how it comes about. So this is our expression, so therefore delta F, I would like to know how the free energy depends on M. If it turns out that the free energy does depend on all the components more or less, then my assumption, my conjecture will be wrong. Because according to my conjecture, it should only depend on the change of the other parameter of magnetization along this, the first direction, because it's a radial direction in this case. And should not depend on M2, M3, and 4, and so on. Let's see how it comes about. That's a very simple calculation. So it is 1/2 M A. Here I write M naught. So yeah, by the way, just I forgot to tell you, it's absolutely clear. Just a second. Just a second. No. Generally speaking, yeah. So M I can represent in the way M1 plus M per. This is what I will do when M per has only components from 2 to n. All right? M1 is just the component of this vector. If I don't have M per, this means the perpendicular component is absent, then I'm only considering the longitudinal fluctuations along the first axis, which is transparent, and we know the answer. But so we need to take into account M per. What is important that M naught times M per is 0. So this is plus M squared and 1/4 V M naught plus M squared and again squared. So this is 1/2 A M naught squared plus twice M naught M plus M squared, that's fine, plus 1/4 V. Now I have to square this expression. I take the square of this, I take the square of this, and I don't take the square of this because it would be a 4th order correction, which I'm not interested in. Then I take the double product, this by that. It will give me 4 M naught squared, M naught times A, M, correct? Squared, right. It is from here, right. This times that. I will have to take twice M naught squared times M squared. All right, and I don't need to calculate, to multiply this by that, because again, will give me a higher order terms. Very good. Right. Right. Okay, okay. Yeah, so the first terms which don't depend on M will give me the contribution to the free energy in the ordered phase. Right, because this delta F is the difference between the free energy in the ordered phase and disordered phase, because as long as it's the free energy when in the paramagnetic phase. So therefore, there will be some constant depending on the naught square, which I'm not terribly interested in, these two terms, of course. Right? Now, they will also be terms which look as follows, linear in M. Let me collect them. They give me A and naught. This is from here. And there is one more term, linear in M. This is the one. Plus B M naught squared. Yes. And again, a naught. Excellent. So I can rewrite this as M times a naught. And remove this, and remove this. And I see as what is written and is practice identically 0, because this is the self-consistency equation for the ordered parameter in the ordered phase, which is quite clear, because if I had minimized with respect to M, that would be the same as if I had added a small deviation and then linearized with respect to M. What comes out in this linearized term is just nothing but the first derivative. It's exactly the case. So therefore, I'm not interested in the first order terms. This is 0. Now, in the second order terms, what I have coming from here, I have a term which is 1/2 A M squared. I have this term. This is important. It will be B M naught times M. This is squared. This I have already taken into account. And plus it will be 1/2 of B. 1/2 of B. M naught squared. M squared. And I should keep in mind that there is a relation which is the solution of the self-consistency equation in the ordered phase. So in other words, M naught squared is fixed. The length of this vector is fixed. Right? Now, let us see what we've got. In fact, it's a very simple, if not to say trivial calculation. Yeah.
What's the reason behind calling it a self-consistency? Is it just because we are dealing with the ordered phase?
What is the reason of what?
Calling it a self-consistency.
No. We are in the Midfield theory. The Midfield theory fixes the length of the vector. And it fixes in this way. The length of the vector is determined by the minimization of the free energy with respect to the order parameter. It will start prescription as any Midfield theory, any Landau theory is a theory which is valid under assumption. Then you have to minimize the free energy and find out the most probable distribution. So therefore, the free energy takes its minimum value for this value of the length of the ordered parameter, which is important. The length is known unambiguously. The direction is not. That's the point. We are talking about now the direction. So m naught is fixed. So let us see, let us combine the terms. So if I single out the m term, m squared term, right? What do I have? I have 1/2 of a and plus, again, 1/2. So 1/2 goes out. It is a plus b, if everything is correct, right? M naught squared. Good. And then I don't like the coefficients, to be honest. This 1/2 here, why did I have this 1/2? Oh, that's right. 1/4. Let me check with my notes. I don't like the coefficient. It's another called cancellation, which to me appears as redundant. Okay, let me check with my calculations. No, it's everything's fine, everything's fine. So far so good. So yeah. No, it's everything's fine. It turns out to be fine. And then there is an extra term plus b m naught times m squared. So it's again, we see this condition. And precisely this expression appears in the first term, therefore it also vanishes. Now, as you remember, I said that your m is the part which is the longitudinal with respect to the direction of spontaneous magnetization. It was the first axis. And the transverse one, the contribution of all the others. But the transverse is perpendicular to this one. So therefore it doesn't contribute. So what remains here is b m naught squared times m1 squared. The first component, the projection onto the spontaneous magnetization. In this picture, I'm drawing it again for the first time, third time. It is this. So you realize that what you can write down, it's alpha, proportional to alpha, absolute value of tau, and the projection of n. Okay, let it be as it is, m1 squared. So the free energy does not depend on transverse component of magnetization, of the fluctuations. Transverse fluctuations do not contribute to the free energy, which precisely means the full degeneracy. Right? So if I look at the shape of the free energy is some constant plus another constant which is positive times m1 squared. In other words, it describes a potential well in the m1 direction, and therefore there will be a certain energy parameterized by this number b, which is positive, and according to that there will be a finite correlation length. I will call it sine parallel. The longitudinal fluctuations are characterized by a finite energy and the finite correlation length. But the free energy does not depend on M2, M3, and Mn, which means that the free energy is fully degenerate with respect to any transverse motion. the fact that the energy, the free energy, does not depend, it means that it's like you have a plane, the surface of this desk, and you put the ball, and you give a ball a small kick, just to enforce it to slide across the surface of the bullet. If you ignore the friction, it will go with the constant speed, and all the positions are equilibrium positions. You can stop it at any point, it will rest ad infinitum. The same is here, just the same. Full degeneracy. So, of course, in this case, you can say that there is no transverse characteristic energy scale. The transverse frequency should go to 0, and correspondingly, the transverse correlation rate should go to infinity. Because when you send k to 0, it means that the psi goes to infinity. When momentum goes to 0, the corresponding length goes to infinity. This follows from the general properties of Fourier transformation. So this is kind of manifestation of very simple but elegant, I would say, elementary, but very elegant, of the essence of the Goldstone theorem. Okay, now we turn to something more interesting. So far we used to completely ignore fluctuations. Now the fluctuations will be basically ignored in another sense, which we will discuss a little bit later. But the most simplest fluctuations, which might have been accounted for within the Landau expansion scheme, or Midfield scheme, if you wish, are those which are associated with the non-uniformity, non-homogeneity of your order parameter. Your order parameter is not obliged to be homogeneous across the whole sample. It may vary from point to point, and these are precisely what fluctuations are about. The value of the order parameter in the coarse-grained picture, we already discussed it last time, are such, the value may vary from point to point, and if you produce this coarse-grained picture, which is increasingly valid if you are close enough to the transition point, because all these inhomogeneities will be look very slow as compared to the minimal energies, minimum X scale, like lattice spacing and whatever. In all these pictures, we can account for at least weakly inhomogeneous configurations of the order parameter. So we can say that what happens if our order parameter m, we are coming back to the Ising model, which is the simplest, m is the scalar function now, but x belongs to an r-dimensional, d-dimensional Euclidean space. It's a hypercubic lattice in the original formulation. Now it is a simply Euclidean space, because this is a coarse-grained quantity. And on top of that, we have also gradients of this function. Right? So therefore, we can expect, and that's precisely what has been done by Ginzburg and Landau many years ago, in the 30s, we can expect that the free energy will contain information not only on the value of the order parameter, but also on the way it varies from point to point. Which means that the free energy is no longer a function of the order parameter, which used to be uniform across the whole sample. But now it's functional. Perhaps I expect that you know what's the difference between functional and functional, right? A functional of m of x, which means that this functional should depend, first of all, should represent an integral over a d-dimensional space. It should necessarily contain those pieces which we have already discussed, The only difference is that now we will explicitly indicate the dependence of the other parameter of the accordance, but this is not all. I would like to include terms like this. The gradient terms. The gradient terms, the lowest order of the gradient terms can be immediately fixed, so to speak, if you use one of many restrictions which are imposed. The most general restriction, which is always so, is the global Z2 symmetry. The global Z2 symmetry, if you have a gradient of M, tells you have to have gradient of M at least squared, not the first order, because of the M to M symmetry. There is another reason, and if you had written something like this, that would be a bad news, because a linear term cannot appear in the expansion of a scalar function, f. Therefore, you would have to multiply it by some other vector d to make a scalar. But then the presence of this vector, d, and a finite first order gradient will tell you that you have broken invariance of your space with respect to rotations. You have specified certain direction, d, in space, and you have no right to do it, no reason for to do it. It can't be justified. And finally, physically, if you have a finite gradient appearing in the first order, the system is absolutely unstable because it will fall into the state with the, it depends on the sign which is in front. The presence of the gradient will tell you that the homogeneous state is completely unstable. It will accumulate the particle at one end of the sample and make it empty for the rest of the sample. So the standard uniform states will never be one of the possible states. So therefore, what we write here, it is 1/2 C gradient of M squared, where C is positive. C is necessarily positive because creating an inhomogeneous state must be costly. Must cost you something. Costs finite energy. Every time you go from a uniform state to a non-uniform state, you increase the energy because the minimum energy state is a state with all the spins up, and if you overturn at least one, it costs you an energy. So therefore, and this already, in the smooth picture, will give you something like this. If I translate this picture into the continuum, for continuous function, it will be something like this. Every time you have a bump or hump, doesn't matter what, you pay the energy. All right. Now we can, no, we know there, okay, so for A we have the same definition. Alpha is positive, tau is tau, and B is positive. On top of that, we have a magnetic field term which we will make a local. In other words, the magnetic field which will be applied to our magnetization may not be uniform. It may be local, non-uniform, depending on the point, generally speaking. Well, so far so good. So this is an expression for the free energy as a function of magnetization and its derivative, which for any given values of magnetization as a function of x represents a non-equilibrium state. It's a macroscopic state, but generally speaking, non-equilibrium state. You can imagine many states with a given distribution of M and its derivative, which are accessible theoretically as a metastable states thermodynamically, but not the states which are absolutely stable. To make them stable, what you have to write down, previously you would differentiate the energy with respect to the other parameter, but that was possible because the free energy was a function. Now we have a function. So correspondingly, the derivative should be functional. And the functional derivative is denoted by this. Let me remind you what precisely is meant by this procedure. How we should accurately define the functional derivative as opposed to the standard derivative of what's written here. So what you do is the following. You assume that you have an m of x, which is some equilibrium, but yet so far not exactly known value of the other parameter, and some deviation from it. Now the procedure becomes clear. You want to substitute this into this expression and single out all the terms which depend on delta m in the lowest order, specifically in the first order. It should be some kind of integral with the expression, complicated expression, times delta m of x. In other words, if you build up delta f as f minus f as f and minus f and naught, and it will take the form, the integral ddx of some expression, call it f, okay, with me dependent on, times delta m of x, right? What is written here, if such a representation is possible, is precisely the definition of the functional derivative. Delta f delta m of x would be this f of x. I don't know specifically how it looks like. It's subject to calculations. But that's precisely what is meant by the first functional derivative. Because you have gradients, you generally will also have gradients of this object as well. But you have to get rid of those gradients by integrating by parts and reduce everything to this form. If you can do that, then what stands in front, inside the integral, represents the first functional derivative. Let us do it. The standard terms, this, and that, are trivial. You proceed exactly as you would do in case of standard function. The problem is with this term. You don't know what to do. Right? So let's consider it more accurately. So let us consider the integral over x. I will skip this notation.
Excuse me.
Yes?
What is m naught in this case? Do we know how m varies with the x that you are putting there? Like,
I don't understand the
I'm
question.
asking.
Say it again.
You are writing delta f as f of
This one?
the second equation, the next. Yes, and what is m naught in this case?
No, this is as a function of x, and this is a function of x. This is for arbitrary m, and this is for the equilibrium one. I assume that the deviation from equilibrium is small. I'm looking for the shape of this function. To establish it, it should satisfy a certain equation. To derive that equation, I have to write down the unknown quantity n as something I'm looking for, which is this one, plus a deviation. How do you derive the derivative in the standard calculus?
It is limits.
So you have f(x) plus delta x, right? Minus f of x. What is this? This is precisely what is written here. And then you expand.
Yes.
And you find out the result to be delta x, df dx, plus what? Plus correction of the higher orders, which you ignore. Because you go to the limit when delta x goes to 0. I'm doing just precisely the same in the standard procedure. It's minimization. Right. So let us check the situation with the first term. So we have gradient m squared, which is the integral over x, gradient m plus gradient delta m squared. It will give me the integral gradient m squared plus twice gradient m times gradient delta m plus terms that I'm not interested in because they are of the second order. This will give me what it was in the beginning and will be cancelled when I build up this difference, of course. So we're discussing the fate of the second term. In the second term, I do integration by parts, and I reduce it to minus twice integral over x, Laplacian, the Laplacian of m times delta m. Integration by parts. Is it clear? The free term vanishes because of the boundary conditions. I assume that there are no gradients in my simple on the boundaries, because if there are in the infinite limit, they will contribute to infinite energy. This is something I should have said in the very beginning. If I have a sample in which I allow the order parameter to vary in space, being a consistent physicist, I should assume that the gradient along the whole boundary of the sample should vanish. If it does not, in the limit, when the length of the system goes to infinity, when the boundary becomes infinite, you'll find out the infinite contribution to the energy. Everything will diverge, and you can throw all your calculation into the basket. Its price will be zero. Right. Yeah, so we see the appearance of this coefficient 2, the minus sign, and delta m. Now, therefore, I immediately realize what is the structure of delta f of m, which is defined already here. It is the integral d dx minus c Laplacian of m, Laplacian of m, plus a m of x plus b m to the third, and minus h as a function of x. And then everything of this should be multiplied by delta m of x. And this is the end of the story. This is how the first variation of the free energy looks like. I didn't do all these calculations here because they're transparent, they're different, they're self-evident. As we said, this is the function f, which is here, therefore the first derivative of the free energy, delta f, delta mx, should be minus c Laplacian of mx plus a mx plus b to the third minus h of x must be equal to 0. And this is the famous Ginzburg-Landau equation. It has been used in the theory of superconductivity, it has been used in the theory of magnetic materials, for superfluid helium, and so on and so forth. This is the new equation which you have to deal with if you want to incorporate inhomogeneous configurations. Right. Now we're turning to correlations. Why do we deal with inhomogeneous configurations? Because we would like to know the following thing: if I, at some point of space x, I change the other parameter in some way such that local value is m of x not necessarily equal to m naught. But I know what is the value of mx. I have a special device which tells me what is the value of this other parameter at this particular point. Then I move from this point to some other point of space, which of course is the point of my sample, and ask it if I measure the other parameter at another place, while I know what it was in the beginning. What is the probability for the other parameter to take value mx prime under the condition that its value here like this? Under the condition is the most important part of the story. It's something which is not simply the probability, it's the conditional probability. Such probabilities are described by correlation functions. X minus x prime, average m of x, and x prime. This quantity is exactly what I mean here. It's not the average of this one. But you can nevertheless reduce the problem to a calculation of the average value of magnetization. But then you have to do it in a smart way. You have to be smart enough to understand what you need to do. How to enforce the configuration to satisfy your requirement. I know for sure that here the other parameter is this. What is the tool which can fix the other parameter at some point, in your opinion? What is the tool? What is the physical quantity? What is the physical device, if you wish? What is the physical field which can fix the value of the other parameter in the desired fashion, in the desired point? What is that?
The physical things are external field and...
Which field?
Magnetic field.
Yes, exactly. That's the point. You can imagine the field whose extension, spatial extension, is reduced to a point. Of course, this is impossible to accomplish, but the distribution of this P field as a function of distance around some point x, absolute value, should be extremely as small as possible. And don't forget, please don't forget that the magnetization of x is not a single spin. It's the group of spin. It's a coarse-grained picture. Sure, therefore you have some spin, you have some magnetic field with some distribution, you will have some distribution of the magnetic moment, but all you will sum up and say, okay, at this point I have the corresponding value of m of x. Right? Right. So therefore what I do the following thing. I look at this equation, the Gisborne-Landau equation, and assume that my magnetic field is a local field which has the following structure. Here delta dx is the d-dimensional Dirac delta function. I'm sure you all know that. So you live in a d-dimensional Euclidean space, maybe 1, 2, 3, 25, 177, and so forth. And this is delta function in that space. Excellent. Now what you need to do is to calculate what is the effect of your magnetic field upon the uniform picture. Uniform picture would correspond to the case H is equal to 0. And then you know that in that case, all configurations must be uniform. So the only reason for inherent need is the magnetic field. So you apply the magnetic field at some point of space here. This is the magnetic field, H, delta of x. And you fix the value of your magnetization, which is induced by this say, sufficiently strong, but it should not necessarily be very strong. What you expect to happen is your magnetization should decay as long as you are deviating from this point and go inside the sample. Because if you switch off the magnetic field, you have a uniform magnetization. Whether it will be a paraphase or a ferrophase doesn't matter. That will be a uniform phase with uniformly distributed magnetization. So the only reason for non-uniformity, for non-homogeneity, is the magnetic field itself. But since the magnetic field acts at this point, it will induce magnetization locally. But then you understand that there are some correlations between the directions of the spins. So this information will spread to the nearby spin, and then to the next spin, and so forth and so forth. Every time you go away, this information would be characterized by a lower and lower amplitude. It will start decaying in space, it's for sure. Right? Because this is an excess of your magnetization, which is here. So therefore, the logic of our discussion is as follows.
So about this decay of information, let's suppose we said that, okay, we try to create a point magnetic field, and then it will decay. So this decay is because of the lack of information between one spin and other spin, or the decay of this the field?
No, the field is a probe. The field only induces the imagine that you are in a paramagnetic field. So forget about ordering. You are in a paramagnetic disordered phase. Right? On average, the magnetization at each point is 0. Paramagnetic phase means just that. Now you apply the field. At the point when the field is applied, you have a finite magnetization. Right? But even though you are in the paramagnetic phase, the spins are correlated. There is certain distance when the information from one spin goes to another one.
Okay.
Right? So once you have perturbed your system and created a local perturbation and the spin locally got polarized, this polarization will start affecting nearby spins. How far you can go in this? As far as this correlation length would keep you informed about the existence of this point. So therefore, there will be a cloud of perturbed, non-zero magnetized spins decaying as a certain function. We'll find out which function is that. Is a function with distance. And this distance from zero, from the location of the field up to the point when information is still there, is called the correlation method. We are coming now to mathematically correct way to define the correlation length. So far, it was a kind of philological definition, not physical. This is a kind of attempt to do everything physically. So we assume that when h is equal to 0, m of x is a naught. And m naught is determined by the equation a plus b m naught squared is equal to 0. We don't need to derive it again because we have done it so many times. Right? So therefore, now I apply a small magnetic field, a weak magnetic field, assume that Mx deviates from this value, equilibrium value, to a small degree, such that M1 is much less than M0. Well, it will be tricky. It doesn't matter. It's not a good definition. I should put a cross here, because if you are in a paramagnetic phase, your M0 is 0, so therefore this doesn't make any sense. But there is a typical scale when M0 varies, and therefore the perturbation should be small as compared to that scale. You can find out what that scale is. And then what you do, you simply linearize this equation. So you write down minus c Laplacian of what? This is a constant, so you have right down here M1. Right? Now you write down this term, which is A M naught plus M1. This depends on X, this depends on X. Plus B M naught to the third plus 3 times M naught squared M1 plus higher order terms which I'm not interested in, again as before, and minus H is equal to H. That's fine. Now this cancels that exactly. This is the equilibrium condition, right? So what we have is minus C Laplacian M1 plus A plus 3B M naught squared times M1 is equal to H of X. Well, I can write down H delta X. Now you have to recall, to refresh your memory, because the expression written in these brackets must be familiar to you. You perhaps remember, or at least you should, that the zero field magnetic susceptibility in the Landau theory or in the Midfield theory is given by this general expression. You can check with your notes or with the lectures. You remember how it was derived? You simply write down the homogeneous self-consistency equation. You differentiate magnetization with respect to the magnetic field. You have included the magnetic field, right? And then you derive this expression. So when the solid phase M naught is 0, it's 1 over A, 1 over alpha tau. In the order phase, you have the relationship between A and B and M naught. And again, have minus 1 over twice A. So this is, you should remember. So this is the expression of for the susceptibility. So what we can do now is to do the following, to write down the equation like this. Minus delta squared plus kappa squared times M1x is equal to H divided by C delta function. When kappa squared is what? The kappa squared is so 1 over C and kappa, and that's it. This is how it is. All right. A positive quantity determined by this susceptibility. Susceptibility is positive by definition. It's a paramagnetic susceptibility. The system is always a paramagnet from the point of view. It's not a diamagnet, it's a paramagnet. How to solve this equation? Who has an idea? What? No, please keep going. You have an idea.
It's
Tell me.
parabolic differential equation.
All right. So are you familiar with this kind of equation? Have you met any?
Green's functions.
Green's functions. Oh, how do you know about these Green's functions? Did you meet these Green's functions for the first time?
Mathematical physics.
Mathematical physics. And what about the course of electrostatics?
Yes.
Yes.
Thank you very much. That's the answer. This is nothing but the Poisson equation. That's the Poisson equation. How do we solve it? I remind you that there is a representation of the delta function in terms of the d-dimensional integral over momentum. This is a very, very useful representation of the delta function in terms of the integral. Right? Yes. What you can do now is the following thing. You can write down the answer, a formal answer, the formal solution as an action of the inverse operator -1 times h divided by c, and this integral. Of course, this h divided by c can be pushed outside. I inverted this operator and wrote down its inverse. Now what you can, the way it's being done is the following. You know the action of this Laplacian operator on the exponent I prime x, and of course it's minus k squared times this x. In other words, k squared is the eigenfunction, minus k squared is the eigenfunction of the Laplacian operator. So therefore, if you look at the reciprocal inverse operator, all you will need to do is to write down the corresponding eigenvalue of this operator will be k squared plus kappa squared. You agree with me? So for the eigenvalues, the standard, the simple algebraic rule holds. It doesn't hold here as long as you're differentiating. You have to carefully define what is this. But to find out the action of this operator on this function, it's sufficient to find out the action of this operator without -1 of this action on this function, and then to divide by it. That's a mnemonic rule which you can check. Now this is particularly simple because this integral can be easily done using the residue theorem. You've done it many times, I'm sure, since you know the Poisson equation. You know the answer for sure, and the result would look like m1 of x will have the form, it will be h, if I'm not mistaken, 2 pi and c. Coefficients you can calculate by yourself. Maybe not 2 pi, but 4 pi. Yes, exactly. It's not 2 pi, it's 4 pi. It's 4 pi c. Exponent minus kappa distance divided by the modulus of x by the distance. So what you can see here is the appearance of the length scale in the problem. Let me call x modulus x by r minus r divided by psi. Rank psi is 1 over kappa is the square root of c times the susceptibility. So what we find is something that what we normally find when the point-like charge gets screened due to the motion of the nearby electrons, and the nearby electrons produce the screening due to the appearance of this kappa square, and this is what happens in electrostatics. Physics is universal. Many things happening in electrodynamics and electrostatics are repeated in this physics, in this part of physics, because mathematics, the background is the same, the structural equations is the same, therefore the physics is very, very close, very similar. So the inverse kappa determines the length scale, and this length scale is square root of the susceptibility. You remember that your susceptibility was basically 1 over tau, and therefore what you have here is 1 over square root of tau. And that determines one of the critical exponents in the theory of phase transitions called mu and the Midfield approximation mu is 1. It is divergent when you approach the critical point, as expected. But you observe another thing. If you use this relation, you can see that your susceptibility is proportional to psi squared. Right? And this very much supports our original idea that of primary importance is not the susceptibility or specific heat. Of primary importance, it is just this way. Why? Because the larger is psi, the more degrees of freedom are involved. The most striking is the difference between strong fluctuating system close to a phase transition from the original, say, paramagnetic system, which was far away from the phase transition, higher temperatures. Well, small details, tiny details at short distances were important. Now they are not. And we are passing to the thermodynamic limit when the infinite number of degrees of freedom determine a completely new stereotype of behavior of our system. So this will be very much used in what follows, and this is the expression for specific heat, excuse me, the susceptibility as a function of expressed in terms of the correlation function. Now, this is already the behavior of the correlation function. But the correlation function, as I mentioned already, has a slightly different definition. It doesn't involve any magnetic field. That doesn't need to be done. In fact, the correlation function is just this average. And there is a straightforward way to estimate the behavior of this correlation function. If, for instance, you simplify your problem and say that you are above Tc, and you restrict yourself by the lowest order expansion of the free energy. In other words, if you write down delta F as a function of m in the following way, it's ddx, I will write down c divided by 2 gradient of m squared plus a divided by 2 m squared, full stop, nothing else. This will be only valid if tau is greater than 0, if I'm simply after to understanding what these fluctuations are doing. Now my model is Gaussian because it contains only the second order of the unknown field. Right? This is the free energy of a Gaussian model where the field m of x is characterized as this distribution. The good question is how, using this, how to calculate this. So I originally was planning to do it today, but there is no way of doing that because actually we have done everything. I would like next time I will spend some time to show you some technical details because otherwise it is tricky. But you can look into the lectures and understand what's going on. So you insist on saying that there will be no lecture? Okay. Not this one. This is to stop.